Hi, everyone. Thank you for joining. We are super excited to be with you today to talk about synthetic data. My name is Omar. I'm the Director of Product Marketing in Parallel Domain. I've been working in AI machine learning for the last 14 years, assuming Director of AI positions in different companies, worked with different kind of projects, especially computer vision projects, where at least 50% of the projects I was pursuing did not complete due to the fact that we did not have high quality labeled data. That's why I was super excited to join Parallel Domain last year. And I'm going to share with you why I'm really excited about that more today in this webinar. Phillip, do you want to introduce yourself?
Hey, I'm Phillip. I lead the machine learning team here at Parallel Domain. Joined a little over 2 years ago. And before this also worked in data labeling. So I know the pain of getting good quality labeled data. Also the reason why I joined a synthetic data company. And I'm going to keep it short and hand back to you, Omar.
Awesome. Thanks, Phillip. I mean, I'm sure everyone in this call in this webinar have heard about synthetic data somehow, right? Like it's a famous topic. Gartner talked about it. Everyone is talking about it. Here's the bottom line. Synthetic data is definitely useful. The trick is how to get real value out of it. Whether you're using it to train speech models or tabular, vector models, you're trying to predict something, or fraud detection, or computer vision models, or perception models, which is going to be our focus today. It's not that easy to get real value out of it in terms of machine learning performance. At the end of the day, you want to use synthetic data to boost the performance of your models, and that's what we have discovered. It's like a combination of art and science, and this is exactly what we're going to talk about today. There are so many different practices to get real value out of synthetic data. A major one is the idea of tweaking and iterative design. The idea of continuously iterating with your data set and tweaking those parameters and testing with your models. And that's exactly what we're going to cover today. So just wanted to share this up front. This is going to be more or less the outline. We're going to start with an introduction to synthetic data and show you different examples of what synthetic data are and why they're useful. We're going to share some use cases, some of the most common use cases that we see with our customers, and some success stories that we have seen synthetic data really driving amazing ML performance. And then we're going to start gradually going into our topic. We're going to talk a little about the domain gap, this gap that exists between synthetic and real data, and what kind of hyperparameters that we can tweak to reduce that gap, and the impact of tweaking those knobs. We're going to show different examples for knobs that you can turn and change values. And finally, how to enable rapid iteration. We're going to close with a Q&A. So please, again, if you have any questions, keep them coming. Okay, so classical machine learning, ML teams spend a ton of time to get the right data, develop their models, ship them to production, right? You guys know this better from me, right? Like if we take an example of autonomous driving, you spend a lot of time on the road collecting data, curating this data, labeling it, providing a lot of labels, QA, training models, etc. It takes a lot of time. We've found that on average in ADAS and autonomous vehicle systems, this could take up to like 6 months or something. In addition, the data is so skewed, right? Like you have a lot of examples for the common classes like cars and pedestrians. But what about like dogs and construction sites and cyclists and other edge cases, long tail scenarios that you'd like your models to detect? The data is usually skewed, and there is a huge class imbalance here. And this is exactly what we're solving in Parallel Domain. We provide technology that enables machine learning developers, especially focusing on perception tasks, to better train and test their perception models, but 100x faster. And when I say 100x, this is actually a number that we've seen with many of our customers. Like literally, instead of like an average cycle of 6 months, we can shrink this down to from like 1 to 6 hours. And we provide different products to do that. Whether you want to generate data for training or do daily regression testing. And we have a brand new product that we're about to announce very soon, so stay tuned for that. That will help you generate data using Python and natural language. So what exactly do we focus on? We focus on providing technology for you to generate synthetic perception data. I'm talking camera, LiDAR, and radar, especially helping you to better train and test your models for edge cases or long tail scenarios. So you can see here, you might not have a lot of examples in your data for vulnerable road users, for example, that you can see here, or emergency vehicles, or construction sites, or debris on the road, or pedestrians jaywalking, for example. Although these are examples for scenarios that you'd like that we have found that a lot of our customers usually want to have more and more examples, like thousands or tens of thousands of examples, of labeled examples, so they can better train and test their models. The problem is this is so hard to find in real data, and it takes a lot of time to collect and curate and label, right? And these are some examples for what our data look like. These are some of the famous scenarios. Like we work with a lot of customers on helping them better train and test parking scenarios, like you see on the top left, or trailer detection, to better detect the trailer and its position and its relative angle. Also, road debris is a famous case, providing different kinds of road debris with different types of labels, as you see. And road signs, that's becoming recently very important, especially in Europe, for ISA detection. And there are more and more sensors that we provide to, like BEV, radar, orthographic camera, etc. And the good thing that I personally like a lot is the idea of having a lot of labels. Given the data is synthetic, it comes pre-labeled with different kinds of labels, whether 2D or 3D. So you can find here the classical 2D, instant segmentation, semantic segmentation, panoptic segmentation, but also for LiDAR, like 3D bounding boxes, 3D cuboids, instant segmentation, material properties, 3D surface normals, optical flow, you name it. Now, here's the thing. Synthetic data is not just cool. It's producing real results. These are some quick examples for the kind of achievements our customers have achieved with that. Some of our customers achieved 10 to 50% reduction in relative error rate for recall when it comes to sign classification. This is a major use case, especially in Europe, with the new ISA regulations. We have done internal research that has improved the precision, 25% AP improvement on cyclist detection when we added synthetic data to the mix. When it comes to segmentation, we have seen 10% MIU absolute improvement from drone point of view. And for LiDAR, we have seen 13.5% relative improvement of motorcycle detection in LiDAR. So as you can see, it's across the board for different tasks, semantic segmentation, object detection, classification, and LiDAR, but also for other kind of scenarios. Like some of our customers have seen 45% reduction in relative error rate for AP for lane lines. We have recently published a blog post for optical flow showing how adding parallel domain synthetic data can help reduce EPE by 18.5%. And the good thing is that it takes minutes to generate this data set. We're going to show you today how it's so easy with like simple couple of lines of code to tweak so many parameters. And finally, the ability to deploy your perception models literally in 100x faster. So with that said, I want to start gradually moving towards the topic of today, which is iterative design. What you're seeing here is the classical way of doing things when it comes to machine learning development, right? Like you get data, you capture the data, you do the QA, annotation, curation, etc., and then you start iterating on the model, right? You start playing with these hyperparameters in the model. You try different architectures, you try different hyperparameters, and you usually spend most of the iteration on the model part. But what if we flip that? Instead of iterating on the model only, also iterating on the data itself, which is something that synthetic data provides. The challenge is that's not usually easy with real data. Like you cannot go back in time easily and recollect data, relabel it with new rules and new adjustments, but you can absolutely do that with synthetic data. As we're going to show in minutes, it's so easy to keep tweaking those parameters, generate the kind of data that you want. And that's the kind of the mindset we are starting to see shifting in the industry. That in addition to iterating on the model selection, architecture, and hyperparameters, we see a lot of our customers and adopters of synthetic data in general iterating on the data itself. And I have to say, I think, in my opinion, this is an absolute must if you want to get real value out of synthetic data, to find these parameters and keep optimizing, keep tuning it to get better results. And if you think about it, it's a great way of doing things that was not available before. And to lead to understanding what those parameters are and the complexity of these, I'd like to spend some time talking about domain gap. If you look at these two pictures on the right, a real image collected on the streets and a synthetic data image from a simulation engine that is used today, you can obviously spot the gap, right? Like there is a very obvious visual gap between both, but is the gap only related to fidelity or visual, or is it deeper than this? For that, I'll pass to my colleague Phillip to dig deeper on those kind of domain gap parameters. On to you, Phillip.
Nice. So yeah, actually, I'm going to take over this screen share here. So what we found is that domain gap is actually not a single thing. And we came up with like a coarse ontology here to actually break this down into sub gaps that explain what's different between those images. And what we noticed is the difference is not just on the input domain, so the image that you input into your model, but also on the label domain. And we're now going to go over several of those gaps here and show some examples to just motivate how would we go about finding out which parameters on our data to tweak, because these sub gaps like give you a good hint towards what to tweak in our system to reduce that gap. So just starting off with the input domain here on the sensor side, very common one is the color distribution. If you have a default image here on the right coming out of our system, and this is a famous image from Cityscapes, you can see there's a clear difference in the colors, that the Cityscapes has a more green tint to it, and it's something that usually we need some customer data to tweak because we need some examples on, where do we need to shift this? This is very sensitive to the actual sensor that you have, deployed in your vehicle. And it's something, if you don't address it, neither in, by applying on your synthetic data, nor doing as an augmentation during training, that's something that definitely will impact your model performance, especially between training and validation. Another thing would be sensor noise, and I hope everybody can see the difference here. That would be a nice night image with high isotropic noise that you can observe here. By default, if you don't tweak it in synthetic data, you get a very clear night image. And it's also just a parameter that you need to insert into our system to close this gap. And if you don't address it, it actually has a huge impact on your performance. So these small different kinds of sensor noises have a huge impact on generalization from synthetic to real data, or even just when combining both real and synthetic data sets. Another one would be lens artifacts. That's actually something, so there are a couple gaps here that we don't expect our customers to tweak, or like not, it's not something that we need external input for, but that we tweak for our customers. And that's, for example, here, these lens artifacts, as you would see them here at night as well. If you don't tweak them right in your synthetic system, you won't get this blooming effect on your lights, which obviously skew your color distributions quite a lot. And I think we could just talk about different sensor gaps for easily an hour. So we're just going to cut it short here, mentioning distortion, motion blur. There's also extrinsics, different kind of intrinsics that matter. Here on the distortion, just one example on a fisheye camera, where you see, like here on the right, the same scene twice, once with some distortion parameters inputted into our system and one without. And obviously you can imagine how vastly the geometry of objects change if you don't apply these kind of things. So this is just wrapping up the sensors part. I'm going over to the optics. It's also something that we tweak on our side that's not needed to be tweaked by customers, but most of people reference to this as physics-based rendering. And what's very important actually to make this work is that you tweak your materials and light sources properly. And what I mean by this is, since it's called physics-based rendering, you also need to input physically accurate values into your system here. And that's what a lot of our team does. So here's just one example on tweaking metal materials in our system that don't have the right reflectance values, as you can observe here on the left, that you get these very heavy contours on the sun. If you don't tweak this, you get this. If you tweak it right, you see this blooming effect. And it might just seem like a little detail, but especially when it comes to low lighting conditions, this matters a lot. And you can see this in the next example here, for example, if you have street signs or these little bumpy poles that you see in construction sites. Each material behaves differently when light shines onto it. Some of them are very reflectant, like these signs, some are not, especially if you have these little things here where the orange part isn't as reflective as the white part. So tweaking this to correct physical values actually is what makes your physics-based rendering actually physics-based. Then, as I mentioned, it's not just materials, but also light sources. So tweaking the light bulbs on your vehicles to physically accurate values that you would get when buying these light bulbs from your suppliers is also an essential part to make your night scenes, or even just like your dusk and dawn scenes, look realistic. And it's what our team spends a whole lot of time on to make sure that all of this is realistic and good looking out of the box.
Hey, Philip, if you allow me to chime in real quick,
Sure.
what I really like about Philip going through the details of these parameters is this, like this is setting the stage of the kind of parameters you'll probably want to tweak somehow, or at least have control over tweaking when designing your synthetic data sets to ensure you have best value for your model performance, right? I mean, if you look at synthetic data from the outside, you might think, okay, I might just need to make it match the real data visually, right? But it's way deeper than this. And this kind of experience we're sharing, it's based on like more than 5 years working closely with customers and finding about those parameters and building the ability to control those knobs, as you're going to see in the live demos that we're going to show shortly, and why those are important. We're going to show different examples for, okay, we have tweaked some of those parameters, and that's the kind of result or the improvement that we have seen in the ML models that were trained with this data. Go ahead, Phil.
And especially the difference here, just to build on that, there are some gaps that are very complex to tune. So that's something you want to abstract away from users. And some of them that are very use case dependent and something that you need to be tweakable between data sets. So like this whole optics part is usually a constant. It is like assuming we're always rendering under the same physics conditions, you can assume those are fixed and others are not. So here, just one more example of tweaking light bulbs in street sign and street lights, where if you don't do it properly, you won't see the rain reflect in them at night. Just always think that's a very nice image, so keep it in. Yeah, and that's actually leading over to environment. I think Omar's going to take the slide.
Yep. So, we have this kind of blog post on our website. You can go check it out. So we're paralleldomain.com, and if you go to /blogs, you're going to find like a blog post about like best practices when using synthetic data. And in fact, there are a lot of good practices. There are practices related to how to best generate your data. There are others how to best train with synthetic and real and stuff like that. And one part you got to take care of when generating synthetic data is you want your data to match as possible your real life data that you're going to test your ML models with, right? And a part of that is related to the location. Are you training models that are going to be deployed mostly in like urban environments or like, suburban environments or highway or the three of those, right? Like where exactly do you see the gap? Maybe your models are performing nicely on the first two, but not on the highway. So in that case, you generate synthetic data for highways with some aspects to better improve your model in that case. And you can immediately start noticing the difference in the agent distribution, for example, between these different locations that we support, right? So if you're doing urban, you obviously have higher densities of bicycles and cars, etc., versus suburban versus highway, which you can have a lot of cars, but less pedestrians, for example, right? So these are things that you can easily tweak when generating synthetic data. Another one is time of day, right? Maybe your models aren't performing nicely when at nighttime or in like extreme weather conditions or something. So that's another knob that you can get to turn. Weather is another aspect, like, fog, rain, whether it's a sunny day or it's cloudy, etc. These are all examples that could impact your model sensitivity, right? I mean, you can obviously notice the shifting color distributions of pixels between these different, weather conditions or time of the day, which is something that is important to translate to ML models. And that's why we spend like good time making sure that whatever data that we generate match, the real life data in order to reduce that domain gap as possible. And the agent is another story. You want to take that, Kevin? Philip, sorry.
Sure, yeah. Agents actually is a quite important one as it correlates quite heavily with the label domain output, which we slightly touch on after this. And when you think about agents, it's like, in theory, you can place them anywhere, right? So the question is actually, where should you position your agents? Just think about cyclists. Do you always want to position your cyclists in front of your ego vehicle? Do you sometimes see cases where these cyclists pop up on the side of the road? And you might even want to mimic this as well, or you say, okay, it's not just good enough to have them come in cross traffic. I also need them to be spawned on sidewalks. I sometimes want these bicycles not to even have a rider on them. All of these little questions impact the distribution within your data set a lot and matter a huge amount to model performance. And I would even argue way more than what most of your sensor configurations do. Another thing would be when it just comes to agents, the appearance of your agents. So how closely do they match to your target domain agents that you would observe? There's only like a certain level of similarity that you need to achieve, what we saw so far, to make sure that your models generalize. So geometry usually is like a bigger impact on this than the actual texturing of the objects. We can see like some of them might look more similar, like this boom lift, and you might have something like this this caravan, which you could say like on a geometry side, like looks actually way different. Similar would be, you know, just this, I always forget the English word for this, but yeah, this construction vehicle, let's just call it like that. Yeah, and depending on how close you can match this is also something that affects your you know, model performance, reduces the domain gap and makes your models generalize better to unseen data. Another thing that comes into effect here is the density. So what kind of densities do you observe in your target domain? Do you usually see people in huge crowds crossing the streets, or do you, you know, did you deploy your vehicles in a city where there are not a whole lot of people? Very heavily defines like how you also should generate your synthetic data when you know, want to generate people crossing the street. Next one would be something like context. Are there certain agent classes that only co-occur with other ones? So this is a good example here just of people pushing strollers. That's something we observed matters quite a lot, since in like this one is a sample from new images. We also trained models on this to just look, does it matter to the models if we place strollers next to people, like here on the right, or have people kind of touch these strollers? And it matters quite a bit. And so you should always be aware if I care about a certain class, does it always co-occur with another class? Is it even realistic in the real world that it occurs by itself? If not, it's something you need to make sure that it's also mirrored in your synthetic data.
One thing I want to mention real quick for that example, we have been using generative AI, like, you know, some stable diffusion, cool stuff to generate a lot of variety for the stroller examples. And we have seen that it actually does improve model performance for segmentation. And we're going to be publishing about that very soon. So stay tuned. That's a capability our customers are going to have access to. They're going to be able not only to generate data easily using Python, but using natural language too. Like you can type like stroller or, you know, a cardboard box full of glasses or whatever. So stay tuned to this interesting update.
Yeah. So this kind of leads to a next part here when we talk about, so we're going to skip about these first two, label spec and label error domain gaps, since we're going to do a whole thing on this on its own. It's a huge topic itself. But label distribution is quite an important one when we think about designing data sets. And you can break this down into sub gaps between kind of the tasks that you care about for class. So if you do classification for, you know, full image classification, object detection, segmentation, then these differences in class distributions matter a lot to your model performance, since usually the model has a prior on what it will predict just based on what's, you know, the distribution of your training data set. And that's also something you should be aware of, because if you start mixing synthetic data sets that are completely off compared to your validation prior, you might generalize better, but you definitely won't measure this. The second thing is the location. So for some tasks, depending on how you can train on this, if you have to train on full frames versus crops of the frames, the location of certain classes matter a lot. So here's just a heat map of the new images training sets and two PD data sets that we generated of where cars usually appear in images. And you can see here quite heavy bias, usually cars being in front of the vehicle, like this is a front-facing camera. And like this data set usually doesn't have cars on the side, while this one has a lot and this one as well. So just controlling, again, where to position agents very heavily affects your label distribution and therefore also like the, your model. And last one, the magnitude, which usually matters for regression tasks like optical flow, depth estimation, and so on, is just looking at like what's the distribution of your, pure float values in your data set. So here we just look at the floats magnitudes in the kitty validation set and two different parallel domain data sets we generated, where we noticed like this data set here barely has any values higher than 100, while this validation set here has a lot of values higher than this. Biases your model quite heavily, so matching this up, again, is a quite important gap to consider and address. Yeah, so after this, I think I'm heading back to Omar, talk through SDK.
Yep, thanks for the reminder. Yeah, so great examples, a lot of knobs to tweak. Let's see how we can do this in action. Like this is the action part. You're going to see some demos, some cool visuals. And the main way you're going to be able to interact with our technology is through Parallel Domain SDK. This is a Python SDK that enables you to do different things. Today, it can help you ingest our data into your ML pipelines, takes care for a lot of things related to data processing, ingestion, formatting, etc. So we don't need to put energy into that. And the second thing, which is going to come very soon, is the new product I was telling you about that's going to enable you to generate data on your own. I want to show you examples for some of those parameters that we've been talking about. See this video here. What's happening is that we are changing the focal length. We are bringing this kind of warping effect, and it's a common request that we see from our customers. The bottom line, when we work with customers, we want to match their camera intrinsics as possible, right? And this simple line, the field of view equals 80, we are doing that change. We're bringing that warping effect, and we are able to basically bring any kind of intrinsic change to match the actual customer sensor. So that's an example for sensors.
And just to clarify here, like the common request is not that they want sequences with warping images. It's just that we can match any kind of camera intrinsic and distortion that you can think of. So this is just an example of that you can even go as crazy as changing the focal length of your camera while you're driving, if that's what you need, or if that's a cool training procedure that you came up with. Definitely possible with our platform.
Exactly. Yeah, this could be used as the teaser movie or something. But the bottom line, as Phillip mentioned, think of any kind of intrinsic control you want to have. We can bring this so the data is matching your sensor intrinsics. Another common request is like weather, right? Sometimes we work with customers, they have problems detecting things at night, like traffic lights and foggy conditions, for example. So you want to make sure that you're able to tweak and change the weather conditions. As you can see, we're doing this again in a simple line of code where we're defining the time of day to be like day, dawn, dusk, night, etc. You can, control some other weather conditions too with a simple line of code using Python. Phillip, do you want to add anything here?
No, all good.
Cool. And another interesting example is like agent distribution. This is one that's pretty common. Sometimes you want to increase the distribution of some class to improve detection or classification, like vehicles or pedestrians or something. And as you can see, that's what we're doing here. I'm making the density of cars in that example like fluctuate between like 10%, 50%, 100%. And as you can see, the effect here, you can see this live when working with our new product. You can control this easily with a simple line of code and see how your data would look like. And with that said, I'd like to pass back for the 100th time to my colleague, Phillip.
All right. So yeah, what we want to show now is, as you've seen, you have all these knobs to tweak, and there's all these gaps that you can close with this. I'm not sharing much, right? But this also comes with a problem or responsibility, actually. Like you have to think of this just like when picking the hyperparameters for your model. It's very unlikely that you're going to pick the right hyperparameters for your model on the first try. And now, just as a use case or like a real world example on how this looked on our side, we used this new system that Omar just showed to you and tried to replicate one of our public data sets that we, I think, released 1.5 years ago, like the cyclist data set. And what this was about is basically we wanted to improve cyclist detection rates on the new images and kitty example. So our goal was just, let's replicate this data set using this Python SDK. And I just want to walk you through this, like how we did this, and just show like common pitfalls that actually happen when you do this. So just to show some Python code here on, let's just pick that demo. So what we did is like we defined a sensor rig, like gave it a full HD camera, 90-degree field of view, sets for this day, like a day scenario, slight clouds, some wetness and so on, pick the location. And then we said, okay, now let's just place our ego agent on a drivable lane in these scenarios, add some traffic to this at like an 80% density. 100% density means nothing else would fit on the street. So this would be a somewhat dense scene. And let's add some pedestrians. And so I'm just now gonna like define a scenario like this and say, okay, I want 6 frames per scene. I'm just gonna generate one scene. Yeah, and I'll put it to there. What you see now, like it starts generating some data in the background, where it takes care of placing all the agents, sampling from the distribution suite is defined up here. And you know, if I would have put 10 scenes, we would get 10 unique scenes out of this. Yeah, just with those different densities of pedestrians and traffic generators, all with the goal of just mimicking this data set that we generated before. So what you don't see here is like the traffic generator has like a lot of pre-built defaults. You know, it's not just going to spawn a car, but also cyclists, buses, trucks, and so on. This is going to take a minute, but until this starts generating, I'm just going to show the pre-computed one I've prepared. So what you would get out of this is a scene that looks like this. So you see, like we have some pedestrians running around, we have some vehicles, and you can see just a sequence. What we did there in the end is just generate 30,000 frames of this, and then went back to train our model. And what we saw actually is before with our public data set, we got like 50% average position on cars, training only on synthetic data, validating on the new images data set. And now with this new data set, we suddenly dropped performance by, I think, almost 10%, which was quite surprising because we thought, okay, like, should we put in the same configuration as before? And now we get different results. So what we did then is actually analyze, like, let's look at the data set, what changed? And I mentioned before these heat maps, and you saw them actually before. Now I have an explanation why this one looks different than this one is, so this is the heat map from our old data set. And this is the one from a new data set. That's the one from the new images trained data set. And you can see there are barely any cars showing up here. The problem is we simply forgot to place parked vehicles. And I think that this shows quite heavily here on the side. And in the end, it also affected our model, which tended to just predict vehicles in this area here. So what we would do to fix this,
Philip, just showing you real quick. I mean, this is a classical example for the need for iteration, right? You generate a synthetic data set, you train a model, the model is not performing nicely. Okay, guess what? It's so easy to change those parameters, right? So let's see what Philip is going to do and what kind of impact it can drive.
Yeah, so go again here and generate this. So we still have everything the same as before. And we have our traffic generator. We keep it at the same probability. We have our pedestrians. But what we add now is the parked vehicle generator. It's something that you might forget to spawn, but now we say, okay, like within 500 meters of our ego vehicle, start placing parked vehicles. So what changed now is you see the exact same, just as for comparison, that was the scene before, that's after. Since we set random seeds for every scene, as you can see here, we always get the same, so we can perfectly reproduce what happened before. So that really enables us also to easily A/B test, because if we would get completely random new scenes, it would be really hard to pin down what actually changed. You can see now with this new configuration, we get all these parked vehicles here on the side, which then in hand would change the distribution to this. So before we saw barely any parked vehicles here on the boundaries. And afterwards, you could see like the density of the parked vehicles increased quite a lot. And then training on this again showed us, okay, from the performance we saw on vehicles here, we bumped up and actually got better results than before on cars by almost 18% or something, and also improved on the average position. So just having this one knob can make a difference of almost 20% in average position. And we didn't even go like 2 or 3 optimization cycles further than this. So if you really go down the rabbit hole, you can keep optimizing on this data set over and over and keep pushing it forward.
So just to wrap up this experiment, we
Mhm.
wanted to improve rare class detection. We generated data. That data did not help the model a lot detecting that class. We increased the agent distribution. We added parked vehicles, and now we have better performance. Is that correct, Phillip?
Exactly. Yeah.
Great.
So now what I want to show is like more of some case studies we did internally on using synthetic data, and also how we operate as a machine learning team internally, because we already have access to this, this product. And what we do, we iterate on a lot of data sets, and just want to show like how this usually looks like from our side, which we also think is like best practice to get to good results. So what I want to show here now is some examples on the optical flow work that we did, which Omar mentioned before. So what we did here is like we tackled the kitty optical flow task, and wanted to generate synthetic data sets on our side that we can add to the already existing training scheme for optical flow, which includes kitty, flying things, flying chairs data set, and so on, and see if we can improve on the performance of moving objects, because usually we see those models do quite well on the the overall movement that you get from the ego vehicle. But if you have like cross traffic from moving vehicles, those predictions are usually off a bit. And so our goal was to actually improve on that. So what we did, we first tried to identify what are the relevant gaps here to address. And some of them were like, we know that the kitty data set is located in urban, suburban, and highway scenes. So we made sure that we include these kind of maps in our data sets. We made sure that we match the intrinsic location of the camera sensors, the intrinsic parameters of the kitty camera. We try to match the noise of the kitty camera model, and also the color distribution that we can see here from the data set. And just using this, we, with the default config, started generating some data. I think there was 25,000 frames, and started training on this. So you can see here on the top one, which would be the model trained without our data, and the bottom one, including our data. And all of this is basically error rates. So lower means better in this case. And what you can see is like we got better on some of those, but especially on dynamic objects here, we expected a lot more to change. So the good thing is you can see, okay, the data already helped the first iteration, not always a given. But here we see, okay, we got somewhat of a good signal, like let's keep pushing on these dynamic objects. So what we did next is let's analyze why this might not be performing as good as we think it is. So we looked into these magnitudes that I mentioned before, where we just looked on average on each frame in these data sets, how far do pixels move? And what we noticed, the kitty training data set has a lot of pixels that move, 30 or even 60 to 70 pixels between two frames on average. Same for flying things, but you can see here for the PD data set we generated, that it's like a very Gaussian distribution here. So we didn't have any examples of these, very quickly moving vehicles in our data, and same for flying chairs. So our idea was actually we can just skew this or not skew this distribution, make it wider by changing the frame rate of our sensors. Just make sure that we, instead of at 10 hertz, let's just collect at 2 hertz. This way, pixels move way more between frames. And doing this, we got from this data set, so exactly same content, just different frame rate, to this distribution here. And we got a lot of pixels that move like more than 40, 70, 80 pixels between frames. So training on this again will be the top line here. You could see we basically halved the error on dynamic objects this way, just by tweaking this one parameter, which would be the frame rate. So what we did is we identified the domain gap, which was our magnitude distribution was off. We traced this back saying, okay, we can affect this domain gap by tweaking the frame rate parameter. There could be different ways, also increasing the speeds of the agents, for example. But just doing this example, we were able to change our distribution, and this mattered a lot in performance, as you can see here.
Yeah, just reflecting on that one real quick. I mean, optical flow is an interesting one because it's almost impossible to get good labeled data for optical flow tasks with real data, right? And that's a major advantage of using synthetic data in that case. Like we provide, fully annotated data sets, including a lot of labels, more than 30 different kind of annotations, one of which is like optical flow.
Exactly. So yeah, next thing I want to show is just another example on classification or segmentation in this case, where we try to compare different UDA approaches. And the goal was just, let's see how far we can push performance, especially on rare classes here, and also comparing against the GTA dataset, which is so far the go-to dataset to do UDA on 2 cityscapes. So what we did here is, again, like figure out like what are the domains that we need to match. So initially we thought, let's just compare against GTA here. So let's match the same map styles as you would see in GTA, which are urban and suburban scenes. We matched extrinsics and intrinsics of the GTA dataset, and also try to match the distributions of the GTA dataset. So the same amount of vehicles, pedestrians, trucks, and so on, just to have a fair comparison here. As a baseline, and you could see here, that's roughly our distributions line up. This can be quite hard to match, especially if you think about place an agent at a certain position in 3D space and then project it through your intrinsics, like the amount of pixels that actually end up in your camera space vary quite a lot. So matching these pixel level class distributions is a quite hard thing. So just comparing those 2 models then, so it's a UDA approach called Advent. And what we did here is we trained only on the GTA data set and this first iteration data set on our side, and evaluated on this cityscapes validation set. And what you can see here is, like, just from this, we could already improve more than 5% mean IU compared to the GTA data set. So both same model, same training schedule, everything the same, just changing the data set. And then the question was, okay, how do we keep pushing on this now? So we went back to the analytics mode and said, like, what are potential gaps here? And one would be a label gap, actually, that we saw in the Kitty data and the Cityscapes data set. We usually have like these coarsely annotated segmentations, and out of synthetic data, you get these very finely annotated, each leaf by itself. So we just changed that. So kept everything the same, and just simplified our annotations. And this also means like the holes in bike wheels, for example, are just like a circle and not like each spike annotated by itself. Especially on the vegetation, you could see from before it being the 4th most common class, it changed to the 2nd most common since we now have way more vegetation pixels. And then training on this, also you could see like to this, we got another performance improvement of like 2 to 3%. Mean IU, like on the vegetation classes, you can assume like I think it was like 15%. Now again, let's push this even further. So we thought, okay, now let's actually match the cityscapes distributions here to see if we can push it even further. So we took out the suburban maps, only trained on the urban maps anymore. And then we took the class distribution from before, but increased the rare classes. So stuff like bicycles, trucks, buses, motorcycles, and so on, and just made sure that we had more examples of those in our data set. And then training on this again, you could see that we again got an improvement on it. So you can see like an example where we actually did 3 iterations on a data set, and each time we just go back looking at, okay, what else doesn't match? Okay, let's change the data set to add this. Let's change the next thing. You can see you successively keep improving the performance this way.
Hey, Philip, do you want to jump to the statistics calculation part, as we'd like to wrap up probably in 3 minutes?
Exactly, I think, yeah, that's where we're coming at now. So
awesome.
What you see is like, what we did a lot is looking at statistics that are somewhat task related to find out what we need to tweak. And what actually those statistics enable you is that they give you an early feedback loop on the fitness of your data set. And also this way you can, skip actually training the model. And if you know which statistics to look at, just look at those statistics, optimize on those, and generate your data. So your iteration cycles come from days or like even a week, depending on how large your model is, down to actually hours, and you can iterate on multiple data sets like within a day. And now we just want to show like with our platform on how you could do this. So just for time's sake, I'm going to show now computing the stats on like the data set we saw before with the parked vehicles that I showed before. So what we have here is like a live computation of the stats of these data sets. So you can see here, while we generate the data, you can see the classes that we would have in this data set being updated.
I mean, this is super important, like for a lot of the projects that I've worked on, because sometimes you want to like understand what is the problem, like why this is not performing, and doing this kind of slicing and dicing and digging deeper into the stats of your synthetic data is extremely important, especially if you want to like tweak it or change it, as Phillip is going to show.
Mm-hmm. And as you see here, like we can already look at the heat map. So with the data set we're currently generating, so we can see the cyclist distribution, the car, motorcycle. So you can see there are not a whole lot of those in this data set right now. So if we would just go over and say, now let's tweak this distribution by just saying, okay, I want to increase the amount of bicyclists in a data set by 170% and the motorcycles by 130%, and then just regenerate a data set like this. Everything else we keep the same as before. You can also look at the data set you would get like that. And just updating this one. You can see here right away, you get like more cyclists that are located close to the close to the eagle. And you can see like this is actually live updates, like each frame being rendered. You can see like pop up here in the statistics. You can right away see like just a couple of frames in already, we have a higher distribution of cyclists. I can also show you this in this example here, that if you remember the frames from before, which looked like this, we now just change the distribution of the cyclists, and all of a sudden you see, okay, some of these parked cars have been actually replaced with parked bicycles. There are some riders like here. And as I mentioned, since the random seed is the same, you can actually A/B test this on just like exact same scenes, just changing the agents. How does it matter? How much does it affect the performance? Yeah, you can see here that the dashboard updating live while we generate this. And yeah, how we usually use this is we can get early feedback on, do we even see cyclists here on the side? If not, okay, let's change our distribution. How similar does this look to our target distribution? And this always gives you an early out to figure out, is this actually going to work or not? Just here in the class distribution, you can also see the amount of cyclists is way higher than like on this one. So you can see already that the new optimized bias that you introduce into your model that's going to affect your training this way. Yeah, I think, Omar, if you might want to wrap up from here. It's just a quick run through the statistics.
Awesome. Yeah, I mean, thank you so much for attending today. I hope that was useful. We have shown the value of iterative design for synthetic data sets. We have started by showcasing what is synthetic data, how it works, etc. And we have started to introduce the idea of domain gap and the different parameters that you need to tweak to shrink that domain gap between synthetic and real. And the fact that this is not just about fidelity, it's more of an ontology, like things related to environment, sensors, weather, location, label specs, etc. And then we showcase different examples and demos where you tweak some of those. How easy, I mean, first of all, how easy is it to tweak this using our technology with simple lines of code? And then the impact of tweaking those through different examples. We have seen in the case of parked vehicles, for example, once we added those, how that improved the model performance, and the various examples that Phillip showed. First of all, if you have any question, please start throwing questions at the chat right now. We would love to answer them. And while you're doing this, I want to share a couple of things real quick. If you're attending CVPR, you know, the Primary Computer Vision Conference of the Year, we're going to have a booth located just in front of the entrance on the right, beside Meta AI booth here, right? So this is the floor plan, and we're going to have our booth here. The exhibition, I think, is like from June 20 to 22nd. So please drop by if you have any questions. If you want to try this new product that we were showing today, please drop by. We're going to have live demonstrations and you can try it live. The second thing, we are hosting in partnership with our esteemed speakers, a synthetic data workshop. This is taking place on June 18th in CVPR. It's called the Synthetic Data for Autonomous Systems. We're going to have speakers, top-notch speakers from different industry and academia organizations. We have Sanya, the VP of AI Research from NVIDIA. We have Adrian from TRI, and we have speakers from like Waymo, Tesla, ETH, Cruise, and of course, parallel domain, someone here that we know quite well. And finally, we have the Woodscape Challenge in partnership with Valeo. This is a machine learning competition where we're inviting contenders to develop models that can do motion segmentation using both real and synthetic data. So if you go to this URL, I'm going to share it in the chat here. This is the competition URL. You can participate in that challenge. We have extended the deadline to be June 4th. This is a great opportunity, in my opinion, to design algorithms that are going to be showcased in CVPR. We have prizes for the top 3 and to help with autonomous driving safety. So these were just 3 things I wanted to mention. And also, if you want to get your hands dirty with this technology we have shown today, we are offering 2 things. First, we are offering free proof of values, aka proof of concepts, but we call them proof of values. We provide synthetic data that is worth $30,000 for different use cases. So we can work with you on that. We can provide this for free and do this POV for free. So if you're interested, please do reach out. You can reach out to my email here, which is omar@paralleldomain.com, or by filling the contact us form. Alternatively, you can get access to this new product that we were showcasing today. So you can generate whatever data you want for 2 weeks for free. So if you're interested in a pre-POV, getting 30,000 worth of synthetic data, or trying out a new product to generate synthetic data using Python, you can reach out to me or fill the contact us form. With that said, I'm happy to answer any questions if you guys have any, so feel free to start adding them. Let's see. I think I have a question here. How does parallel domain datasets address the concept drift of objects occurring in real-world data? Example, cityscape classes such as walls or fences. You want to take that one, Phillip? I can share what we're doing with the MPI in that capacity, but
I'm not quite sure if I understand. Is it basically the label switch that you would get that sometimes they are labeled as wall or as fences, or
hello, I would like to add regarding that. So concept drift is something like the object, like for example, construction site label is labeled in a somewhat different fashion, and when it comes to real world, there are different variation of this same object. The label space, or the whole domain of this label space changes. So typically, to address that, we need some kind of domain adaptation strategies, but how do we deal with such huge differences in the visual appearance of classes? Rarely classes. Yeah.
So you just mean the variance of like a wall could be a construction site of temporarily puts blockers, or like an actual concrete wall, right?
Yeah. If you look at GTA examples, you will find the wall or fence, a typical red color gaming style. But if it is in real world, it is somewhat different. And how do we address that issue?
Yeah, that's a very good question, actually. So like one answer would be adding more variance in the kind of procedural generation of different walls that we have. We know that like this takes quite some time, which is why we also, Omar mentioned that we have some upcoming updates on Gen AI, and it's also some experiments that we did exactly on this together with MPI, is actually using generative AI to generate variations on these kind of classes to address exactly this. And I think the only thing I can share is that we have something coming up. I don't want to, Omar.
I'm gonna spoil it. Yeah, stay tuned for the new product. We have a lot of amazing things coming, and it's directly addressing this question, as Phillip mentioned.
Yeah. So and that doesn't just go for walls and fences, right? So it's variation on any kind of class, which generative AI gives us a lot of capabilities on changing and varying very easily, while still maintaining all the ground truth, by the way.
Yeah, stay tuned. Still going to come in like a couple of days or something. So I have another question here, which is like, for domain gap, what are some of the most important parameters? So we showcased, Phillip, like we showcased all these parameters. Like what would you consider like the top 3 to 4, whatever?
I think you might have noticed that like a lot of the things we showed today is really just agent positioning and density related. So just thinking about where to place your agents and how to make them behave, or like, especially for behavior, mainly matters for optical flow, because there you have temporal components. So agent placements, therefore also the class distributions that come with this. what we found to have a huge impact is sensor noise, and that can be very plain sensor noise, like matching isotropic sensor noise or like the Bayer noise of your camera. That's usually just something we need to know from your side, like what do you have? And we just input the number, but if you don't match it, it's something you either have to address during augmentations in your training, or it just won't generalize well. Third one is a good one. Like
I would add label specs if you haven't mentioned that already.
Exactly. Right? I think like we're going to do a whole talk on this later this year. But yeah, I think actually the single most important one is actually matching your label specs, and I think it's a research topic for itself. Yeah.
Perfect. I have another question. What is more important for knowledge transfer between synthetic and real data? Photometric difference or diversity? That's the question everyone is trying to answer, right, Philip? I mean, I think the question is like realism versus, diversity. My thought on it is like both are very important. And this question, by the way, has been sent to me only. I can share it with everyone here. So
can you maybe read it again? I'm not sure. I didn't.
Sure. So I've just shared the question again so everyone can see it. What is more important for knowledge transfer between synthetic and real data? Is it photometric difference or diversity? I think it boils down to like realism versus diversity, which I think are both important. There is a lot of research that shows like this important. I mean, some people are saying diversity is more important, but yeah, what do you think, Philip?
I think definitely I would tend towards diversity, because you can do deal with a lot of photometric differences with augmentations. And we found like training GANs to match up, photometric similarity really barely affects your training performance, where just tweaking an agent density value like gives you 10x the performance difference. So my money's on diversity in this case, if you would say like that this falls within diversity.
Another question, what about the quality of texture? Does it also matter?
That's a good one. I want to run an experiment on this soon, actually, where I just want to train on albedo values and unlit scenes. So I don't know right now, but maybe I have some answers soon.
Yeah.
But yeah, we also did some experiments where we just changed, like increased the diversity of textures. And there definitely is a point where it saturates, and like just adding more diversity on your textures, like won't, as everything, like there's a log scale to it usually. So yeah.
Awesome. We have another question. What are some challenges when tweaking parameters? I guess one of those, Philip, is like some of those could impact the others when trying to tweak it, right?
Exactly. Yeah, especially if you think about, like, if you have a scene with a lot of trucks and you reduce the density of trucks, all of a sudden you have more sidewalks popping up or more trees that are visible, which change your distribution. So therefore, it's like, codependent classes that affect each other, like making this tweaking of the data set itself an optimization problem that you need to like have a human-centered gradient descent kind of approach to it.
Is this an art or science? Or both?
I would say it's a science.
Okay. You're a science man. You're always leaning to science, right? I mean, honestly, like speaking about it and experiencing recently, I tend to like look at it as like exactly like the hyperparameter tuning for models. Like we did a lot of hyperparameter tuning, and we're still, and like there is definitely a lot of science to it and evidence and data, but there is also like some form of like knowledge and art that comes after a while. You keep changing these knobs and you keep exploring the impact, and after a while you start getting a feel of like what is the ultimate formula. And that's why I think it's very important to be able to tweak those parameters easily and generate data real quick. And again, back to our point, I think iteration on the model is still very important, but bringing iteration on the data, in my opinion, can unlock a lot of opportunities that are not possible today with real data. And that's why I'm personally super excited about synthetic data. Okay, do we consider this a wrap? I don't think we have any more questions. Thank you again so much for attending today. We're going to share the recording. Don't forget, if you're coming to CVPR, drop by the booth, attend the workshop, participate in the contest if you want. If you're interested in trying out our product, reach out to this email or the contact us form. We can give you 2 weeks access to the new product that we showed today, or a free POV worth $30,000. And with that said, thanks again. You have a wonderful day or evening based on your time and location, and see you soon. Thanks.